Thank you for the invitation. So I talk about basically the review of random metric theory, and this joint work with Zhao Yang Huang, and and then Dubova and Feng Yang, Kevin Yang, and Jun Yin. Right. So it's so I'll start with these Wegener matrices. So this is not geometry, so it's a bit different, but the question is sort of fairly easy to understand. So Wegener matrices, it's n by n Hermitian matrices, and the metric element has mean 0 and the variance 1 over n. Now they are independent, and so this Hermitian can be real or complex. So it's and if the metric element are real and the complex Gaussian, then this will call a Gaussian orthogonal ensemble or Gaussian unitary ensemble. So these are just names, and these are where's it? Is there a pointer here? Oh yeah, here. So these are, and now if you look at the eigenvalues, you in the decreasing order, and then one can see that the eigenvalue distributions, the eigenvalue distribution will converge to a semicircle. This actually was a theorem proved by Eugene Wegener, and then you can see that, and we normalize the variance as 1 over n so that it's between -2 and 2. So this is the standard normalization. I mean, if you choose this 1, then this will become the 2 square root n. So it's much better to sort of scale in such a way. It's this is actually a semicircle, so that's why it's 4 minus x squared. Okay. Now the eigenvalue around this -2 and 2 are called the edge eigenvalue, and the rest are called the bulk eigenvalues in the middle. Now Eugene Wegener, so random matrices was already in statistics called V-shot, but really catch people's attention in the 1950s because of Wegener's work, and Wegener's motivation was in nuclear physics. And at the time, I mean, you think about the people in 1950, and then they try to understand the experiment of this neutron scattering in nuclei, and then the quantum mechanical Hamiltonian is so complicated, you cannot really do much about it. And so Wegener has the idea that because your system is so complicated, then what you should do is just completely forget about all the interaction, all the details of the system. And then he claimed that if you use random matrices like this, and the eigenvalue spacing, this eigenvalue spacing, I mean, here is, you don't see a spacing. The spacing of eigenvalues will have the same distribution as the nuclei, physics. So that's his claim. And it turned out to be actually it's very good models, and so it's incredible that this is correct. So Wegener has idea. His fundamental idea is if you look at systems which are highly correlated, extremely complicated, then he believed the random matrices, the eigenvalue statistical random matrices, actually give you the probability law of highly correlated systems. And this is something very strange because in the classical probability, the classical probability, you can ask what is classical probability? It's basically about independent random variables. So everything will be independent. Everything you're trying to show is even for the weakly correlated system, you want to show it's independent. But we're going to actually ask the question in the complete opposite direction. He says, suppose the system is extremely complicated. You have no idea what's going on. Then his idea is for low system, you have no idea what's going on. Then the good model is actually the eigenvalue statistical random matrices. This will serve as some sort of universal law for the highly correlated system. And this is sort of just philosophically is a bit crazy. It turned out to be to match experiment, and nowadays one can see match experiment quite well. But still, if you look at quantum mechanical system, whatever his claim is still a claim. There's no proof that a quantum mechanical many-body system will become like a random matrix statistics. Okay, so then people try to understand the Huygens thesis. Then they ask the following question, and this was actually Mehta. Mehta wrote a book about random matrices, and then he asked the following question. He asked that now because the Huygens matrices, the Hij. Now this one, if the matrix elements are Gaussian, then you get one statistic. But suppose the probability law of the matrix element is not Gaussian, it's some other probability law. Then do you get the same eigenvalue statistics? So for example, you can have a random matrix which with each element are Gaussian. The other one just flip a coin. And then do they have the same eigenvalue distribution? So this was the question. And the question was the Mehta was already in his book. He asked this question, and then it took a long time. So somewhere about 10-15 years ago, so we solved this problem, and with my postdoctor and so on. Oh, actually, I forgot to say that actually the Terry Tao and Ben Wu also had some partial result in this direction. I didn't write down the detail, but they also have some partial results. Anyway, so the statement is actually the eigenvalue statistics, because now here the eigenvalue were close to energy, but you want to magnify by n. Why do you want to magnify by n? Is because the eigenvalue, you put n eigenvalue between -2 and 2, so their spacing is 1/n. And because their spacing is 1/n, so you have to multiply by n, otherwise you cannot talk about the probability law. So this eigenvalue statistic, if you magnify by this scale n along a fixed energy, then you find that the one you computed the correlation function of eigenvalue correlation function for your matrix H. This matrix H you can think about the probability law is just this coin tossing, and the other one with the Gaussian unitary ensemble, actually they will be the same. Well, I mean, coin tossing is real, then it has to be GOE. So these are called the bulk universality. This means eigenvalue distribution, you cannot really tell the difference between whether they are Gaussian or they are just IID random variables. And now, and the other question is called the edge universality. Now, if you look at eigenvalue near the edge, the spacing actually will change to n to the -2/3. So we magnify by n to the 2/3, and then again the edge universality says the eigenvalue distribution of the extreme eigenvalues, it will be the same as the Gaussian case. And in the Gaussian case, this was computed by Tracy and Widom. And so the edge universality will say that the edge eigenvalue distribution will converge to Tracy-Widom laws. So this is about eigenvalue. And the other thing is about, there's another concept called the delocalization of eigenvector. Now, eigenvector, now you can ask the question, now how is the eigenvector look like? The eigenvector will, it will concentrate at some place, or it's just sort of completely spread out. So complete delocalization says you will completely spread out. You will completely spread out with probability so that it's L infinity norm, and then you even take the super over all the eigenvectors. It's with high probability less than n to the -1 plus epsilon. N to the -1 is the right scale because if they are completely flat, because you are L2 normalized, so each element, the average value of each element is 1/n. So if you prove it's n to the -1 plus epsilon, this means that they are very close to its average value. So they are basically about the same. And here, and actually one can also do another, one more problem we can improve is something called a quantum unit ergodicity. So if you remember, this quantum unit ergodicity, this was a concept by, this was done by Sarnak and Rodnick. In the case of manifold, you will say that the eigenfunction will be equal distributed over the on the manifold for the high frequency eigenvalues, eigenfunctions. But now here, in the case of matrix, it just says that you take eigenvector. If you take an average of eigenvectors component over interval of a certain size, as long as this size is much bigger than 1, then it's close to its average values. So these are the average with 1, it's average value, and little 1 is the error term. So if you take eigenvector and you took a look at a component, you take maybe you take 100 sides, and then you look at the average, then it's become completely flat. And this is called quantum unit ergodicity. So this is similar to the same statement in the manifold case. It's called the quantum unit ergodicity. And there's also a difference between quantum unit ergodicity and quantum ergodicity. I mean, okay, so never mind. So let's just look at this, because this is true for every eigenvector. These are called the quantum unit ergodicity. So actually we can prove all of this, and for the, the question was sort of started in the 1960s or 70s, and so it was finally solved about 10, 15 years ago. All right. So now the question I want to talk about today is about, and after you do the Wigner matrix, so what other question you can do, okay, about in random matrix theory. Now there are a lot of applications of random matrix nowadays in statistics, in data science, in whatever it is, neural networks. It's because actually neural network it's some sort of nonlinear random matrices. It's so there are a lot of these interest in random matrices nowadays. And now the first problem I want to talk about is this deregular graph. So deregular graph is so these are 3 regular graphs. So each vertex has a degree d, and then you take a uniform distribution of such graph. So the uniform distribution of simple deregular graph with m vertices. So this is called G and D, and this random deregular graph, and here is a random 3 regular graph. Now the graph will correspond to a matrices. You talk about this adjacency matrices. Adjacency matrices is if you have an edge between two vertices, then you put 1, and otherwise you put 0. And so these are called adjacency matrices. And now we actually divide by square root d minus 1 because these are normalizations. Actually, it's convenient for comparison with this GOE and GOE. So we always divide by square root d minus 1 just to make it normalized correctly. Now, the deregular graph, these metrics are actually highly correlated. It's not independent anymore because if you think about adjacency matrix, because the degree, for example, degree 3, so this means each column, each row, each column only has 3 elements. So then it's highly correlated because you just put lots of these restrictions, so it's highly correlated. And once again, you put the eigenvalues in a decreasing order, but you know that the first eigenvalue is eigenvector 1 because if you take 1, 1, 1, 1, 1, then each one you only have 3. There's 3 elements is 1, so you get exactly D, okay? And then divide by d minus 1 because this is square root d minus 1 normalization. Otherwise, the eigenvalue is d. So these are something very simple. And then now there's a theorem by Kasten and McKay show that the eigenvalue distribution the random D-regular graph actually will become this Kasten-Marquet law. The Kasten-Marquet law is not exactly semicircle. There's one more term x squared divided by d here, and here in front of it is d minus 1. So you can see if d goes to infinity, this will become 1, and this term will vanish. It becomes semicircle. But on the other hand, if you look at D3 and D5, I mean, this is D equals 3, it's very, very far from semicircle. So for small d, it's very far from semicircle, but when d becomes large, it's actually essentially semicircle. So, these are Kasten, the eigenvalue distribution go to Kasten-Marquet law. But what we are interested, now I want to emphasize something. If you look at this quantity, the eigenvalues is divided by 1 over n. These tell you almost nothing about one eigenvalues. So a lot of people, so suppose you prove something like this is correct, and then you have absolutely no idea where is the location of one eigenvalues, because even the one eigenvalue can be so huge you still don't see it because you divide by 1 over n. So this quantity tell you very, very little about each eigenvalues. Okay, so this was now the question we are interested is called is something called the spectral expander. The spectral expander is a random graph. Is a graph that there's a spectral gap between first and second eigenvalues. So there's for some fixed big constant, and then your family, when your family graph become bigger, it's strictly bigger than some constant c. So these are called spectral expanders, and they are various actually lots of work I'm not going to review, and especially Along and Chigger constant also connected to the spectral expander, and so so the spectral expander is quite a popular tool in computer science. Actually, people in computer science wrote a whole book about expanders. Now the question is for the random D-regular graph, whether random D-regular graph are expanders and how to construct expanders. So there's a theorem by Along and Bopana, in 1986. He says the second largest eigenvalue, because now the first one is a d divided by square root of d minus 1. This we know, okay. The second one will be bigger than 2 minus constant divided by log n. So you cannot, the second one cannot go much below 2. You cannot go much below 2. So you come back to arrange the picture here. So you can see that there's eigenvalue here, but the second one, it has to be close to these two. It cannot go much below here. Okay. So this was Along theorem. Now, so there's a question, there's a graph called a Ramanujan graph. It was defined by Lubatsky, Phillips, and Sarnak. Actually, this is the most cited paper of Peter Sarnak, actually. So they define a connected D-regular graph and is called a Ramanujan graph if all the eigenvalues except the first one is below 2. Because 2 is the best possible. This is Along theorem tells 2 is the best possible. And now the question is whether if everything is really all below 2, then the spectral gap is as big as possible. The spectral gap is as big as possible. This would be best possible spectral expanders. So Ramanujan graph, even though one uses the name of Ramanujan, but actually it's just because it's the best possible spectral expanders. And when use this name Ramanujan, it's because in their paper construction, they use a result of Ramanujan conjecture. Anyway, so this part is the number theory. I don't really know what's going on really. It's but they construct a family of explicit family of Ramanujan graph, but they require the D has to be equal to P plus 1 with P prime. And later on, people extend to D equal to P to the K plus 1. And this was by Morgenstern in 1994. And then, so then Lubatsky asked a question, are there infinite family of Ramanujan graph for every degree d bigger than or equal to 3? So there was a question whether you can do this is correct or not, because their construction is related to prime numbers. And then this problem was not solved until 2013, which was nowadays, this is the first partial result connect to this. They prove that there exist the infinite family of bipartite Ramanujan graph using the method of interlacing polynomials. So this was in 2013. There was this work using this interlacing polynomial idea to prove the existence of infinite family of bipartite. But on the other hand, if you take out this bipartite condition, then then you still don't know. Okay, so on a separate direction, there's a numerical simulation by Miller, Novikov, and Sabelli. Actually, the Sanak talk about this result, but I think that the people really working on the numerical are his student and postdoc, Miller, Novikov, and Sabelli. So what they claim is so if you take a 3 regular graph, you take 3 regular graph, and if you rescale this 3 regular graph in the GOE, and then they seems to fit. So they claim that what they claim is there's a constant C1 times the second largest eigenvalue of random D regular graph, and then you minus there's a possible shift, then it should converge to the Tracy-Widom. So this was the conjecture. This was their conjecture. There exists constant C1 and C2. This is correct. And this was some numerical simulations. And then there was some funny story that actually Peter Sana told me the story. He said he believed that it's almost all regular D regular graph, random D regular graph actually are not Ramanujan. On the other hand, Noga alone believed that almost all random D regular graph are Ramanujan. And so this was and now mathematically, so this is not my result. I mean, this is, so I shouldn't use the main result. Anyway, so Noga alone conjecture that the second largest eigenvalue has to be 2 plus little or 1. And this was first proved by Friedman in 2004. And then another proof, a more general proof is by Bardinev. It's 2015. And there are a lot of other work I didn't mention. Okay, I'm not going to. So for random D regular graph with probability close to 1, the second largest eigenvalue is 2 plus little of 1. And the error term they get is a log n divided by log n squared. I mean, it finds very strange. So how comes something like this? And the reason is what you are doing is you take how do you control the largest eigenvalue or second largest eigenvalue? So what do you do? Because if you look at these spectral results, there are basically only 2 methods. One is by moment method. You take a matrix and you compute a high moment of matrix H to the K, and you take a trace, okay? And then you divide by 1 over K, because so you basically take a trace and then divide by 1 over K. So this is what you do. So because you divide by 1 over K, so you take the higher the moment, then this average of there are n eigenvalue, you take 1 over K of exponent. So when K is large, you start to recover closer and closer to the largest one. So this was the idea. So then but on the other hand, when the moment is very high, it's very difficult to compute a trace. And so that's why they get the log n divided by log n to the square. All right, so this was actually it took us 6-7 years to do this using our method by Green's functions, by Green's function resolvent, and so we can be improved to entry minus constant. Then they also do the extension. They also not just did random deregard, they also can consider random decovering of base graph. And so there are a lot of work here. And in 2024, this exponent was improved to entry 1.6. Okay, but no matter what, but all these results do not answer that whether they are Ramanujan graph, because you don't know this little one is positive or negative. Because no matter how much you improve on this, because you don't know the sign of this one is positive or negative, actually, it does not answer the question of whether the lambda 2 is positive or negative. All right, so here is our main result. Our main result is in last year, 2024. It was actually it's not just the second largest eigenvalue. Actually, all eigenvalues are close to can be computed by using the Kasdan-Marquet law. If you use the Kasdan-Marquet law to compute eigenvalues, then you find that every eigenvalue were close to the Kasdan-Marquet law with error term entry minus 2/3, and this will increase to the middle, will become entry minus 1/3. It's entry minus, there's another entry minus 1/3 put together is entry minus 1 in the middle, and at the edge entry minus 2/3. So it's completely correct. Now, but the key to answer the question of this Ramanujan graph is the following theorem. It's this is joint work with Huang and Mackenzie. Maybe this is 20. So what we prove is the following. It's if you look at the edge eigenvalues. Sorry, I use this mu is this lambda. So I sometimes use. Okay, no, that's okay. So you take eigenvalues of a random deregular graph, and now because the first one is completely outside, so it starts from the second one. So you start to take a second one, the third one, and so on. You look at their probability distributions, and you compute this. And the other one is compute a Gaussian case using the Gaussian orthogonal ensembles. So you find that they have exactly the same probability law with the constant, with the scaling constant A equal to can be computed explicitly. Okay. So this means that in particular, the second largest eigenvalues, you multiply by this constant, then its probability distribution is given by the Gaussian case. But the Gaussian case, it's a Tracy-Widom law. So then you can compute the probability distribution of the second largest eigenvalue exactly in the limit as n goes to infinity. So because now you can compute exactly, then you know that what's the probability, the second largest one, and also the lambda and the smallest one, the absolute value, this is less than 2. What's its probability? Because the Tracy-Widom distribution can be computed explicitly. And then if you using the Tracy-Widom distribution computed, then you find the probability is actually about 69%. So the bet of Peter Sarnak and Alon was actually was a 69% correct, and the rest are wrong. So this was the yes. What exponent alpha? Oh, this one? Yeah. No, at the end, this will be, even when d equals to 3, this A will be positive. So there exists a positive A. You mean this error term? Yeah. This error term will depend on D, but on the other hand, when D becomes small, it's still strictly positive. Okay. All right. All right. So this was the and then I have one page to tell you the proof. So it was it took this was idea we started about 7, 8 years ago, and it took a long time to. So the idea is the following. Now, you look at the Green's functions. One of H minus H is a matrix, and now what you want to show is the trace of the Green's function, trace G divided, will satisfy the self-consistency equation of Castells-Marquet-Law. So self-consistency equation of Castells-Marquet-Law, I didn't write it down. It's slightly more complicated because this function, the Steele transform of Castells-Marquet-Law is expressed like that, but with D finite, this is a bit complicated. Okay, now the case of semicircle is much easier. The semicircle is m squared plus zm plus 1 equals 0. So this is much easier. Now, the idea is to prove that the trace of the Green's function, with a complex parameter z equals e plus I eta, and this eta has to be quite small because you want to detect the eigenvalues. And so when eta is large, you cannot tell the difference between two eigenvalues. So eta has to be close to 1 over n. So eta is quite small. So this Green's function is a trace. You want to show that it satisfies a self-consistent equation of Castells-Marquet-Law. But on the other hand, the Green's function, the matrix is highly correlated. So the matrix is highly correlated, then the fundamental question here is, if you take a highly correlated matrix, what can you do with the matrix? And actually, mathematics, if you don't have you either use no randomness at all, or otherwise you need independence. There's nothing in between. I mean, it's highly correlated. Then, if you want to show something highly correlated, then typically you can just only do the independent. You can either do without using randomness, or the other one, if you want to use randomness, it has to be close. There are some independence. So we managed to find some independence of the random deregular graph. It's the following thing is called the switching, the local resampling. So idea is the following. So if you take a random deregular graph, you take a vertex here, and you take a radius r, and now you look at this ball, and now this ball, there's a boundary edges. So these are boundary edges. So these are boundary edges. So these are boundary edges. Okay. So now these boundary edges, and now, so then you sample. Then you take arbitrary. You randomly choose the same number of edges, like the boundary edges. Now you resample them. Resample means, for examples. So now original one is this one. The original one is this one and this one, okay? So then instead of this original edge and this edge, now you delete these two edges and replace by these two red edge. Now you find that originally it's a 3 regular here, but now after this replacement it's still 3 regular. So this operation will preserve the 3 regular graph. It did not change. So on the other hand, these give you some sort of randomness, some sort of independence. The independence is the choice of this edge to be resampled. These are independently chosen edges. So this is where you gain some sort of independence. You find some sort of independence in the problem. And then the whole problem, the computing the trace of Green function and so on, has to use only these ideas of only use this independence, and so you are able to compute you are able to prove that trace of Green function satisfy the self-consistent equation of Castells-Marquet-Law similar to this one. So this was one line of work of random about this random random matrices we has been doing for a long time, and I still have about 10, 15 minutes. So maybe I will tell you a little bit what's the other thing we are trying to do. So for the random deregulator, I'm not going to go to any details of this because this is just, it's going to be very technical and unless you are in this area, so there's no point to get into such a details. All right, so the other question, the one is interested is, so here there's something called the Anderson model. So this is Phil Anderson. So he was a professor at Princeton, and so what he found is he was interested. This probably was the most well-known result of Phil Anderson. Actually, he got a Nobel Prize for this work. So Phil Anderson, he wanted to study the semiconductor, and now so you want to understand why the semiconductor is semiconducting. So the electron Hamiltonian is given by a Laplace operator plus a lambda times v. Now the v, so if you think about it, this Laplace operator is not continuous. You should think about it on lattice, on d dimension, on zd. So these are on lattice. And these are discrete Laplace operator. And these are kinetic energy of the electrons. And then the v are independent random potentials. And then there's a strength, lambda. Lambda is how strong are your impurity. So Anderson claimed that the semiconductor can be modeled by just Laplace operator plus a random potential. It's really it's remarkably simple. And so his observation is if you turn on this lambda, you see, if you put lambda equals 0, the eigenvector of the Laplace operator are just sine and cosine. The sine and cosine are sort of extended because it's everywhere. But once you turn on the lambda, for lambda large, then the eigenvector will become exponentially localized. And you become exponentially localized. So you can there's a center x0 and then exponential x minus x0 divided by L. L is called localization length. And so Anderson claimed that there's an insulator and the conductor transition. In the case of insulator, the eigenvector are exponentially localized, and for the conductor phase, this L is actually go to infinity. It becomes everywhere. So this Phil Anderson's fundamental idea is this is correct. And now, more precisely, the claim is the following. In dimension 1 and 2, no matter for any lambda, it's always localized. But in dimension 3 or higher, for lambda large, it's localized. But for lambda small, and dimension d bigger than or equal to 3, the localization is actually incorrect. You will become delocalization. And in the first case, when the eigenvector are localized, the eigenvalue distribution actually will become Poisson statistics. But in the other case, when the eigenvector delocalized, then the eigenvalue statistics will become random matrix statistics. The random matrix in the box. So let's forget about the edge. We're not talking about edge. And there was the basic idea of the Phil Anderson's idea. Now this question is actually also a random matrix because it's just the randomness is only on a diagonal term. And otherwise, this discrete the plus operator just 1 and minus 2 in the middle. So it's also another random matrix model. But this question, even there was a famous work by Florek Spencer and by Eisenman and Molchanov. And this was, now you look at this, it's almost like ancient time, 1983, 1993. So this is what they proved about the localizations. For large, actually I forgot to say, they proved this for large lambda. For lambda large, you have a localization, which you can prove. And now Actually, but what they need is this potential, random potential V has to be continuous. The case of Bernoulli case, so if the V, if this V is just flip a coin, like Bernoulli is plus minus one, then the question was actually only solved a few years ago. You find it strange. I mean, this is totally crazy. Well, how can people wait for such a long time to answer a question? Because in 1983 was already first proof. And the Bernoulli case actually was finally solved in 2020 and 2022. And this was by Dean and Smart. But they use the idea of a Bogin mechanic of 2005. The Bogin mechanic do the case. The Bogin mechanic do the case of this Laplace operator is in the continuum, and the Dean and Smart do the case is a discrete Laplace operator. So, but despite all this, there is no proof there is a delocalized phase. So nobody know anything about the existence of delocalized phase. Even there's not even one example one can construct it. So now there's some work on beta lattice, but beta lattice is infinite dimension. It's its own tree, so it does not really count. Okay. So now I will just say about there's some magic. So what's the importance of this? Is because there's a magic called the band matrix. So you take a band, so you take a matrix, and with a band W, and now this is n by n, and with a band W. Now these are one dimension look like this, but you can also define this in 2 dimensions, 3 dimension, using each metric label is actually a lattice point on the ZD. So the band matrix, you can define this on any dimension. And so the idea is the Wigner matrix, it's a matrix quite fat because every place you have matrix element. And now the Anderson model is the one you only live on a diagonal. The random is only live on a diagonal. So in physics, if the matrix element live everywhere, is something you call a mean field theory. And if the matrix element only live on the diagonal, it's non-mean field theory. And now you want to show that there's a connection between mean field and non-mean field. And this band matrix is somewhere in between. Okay. So without going to details, I will just tell you there's a conjecture in dimension d equal to 1. One believe that when W is bigger than square root n, there's a transition to delocalization. In dimension 2 is a square root log n. In dimension 3 is as long as W is some big constant, then one believe there is a delocalization. And this was done by simulation or by supersymmetric argument. And then let me just tell you what's the main result, and I will finish it. I will stop here. So main result is if you consider the Hermitian random band matrix with complex Gaussian entries. Now in dimension 1, we prove that when W bigger than square root n plus a constant. In dimension 2, we prove W bigger than n3 is some constant. You want to think about it, C is just epsilon. It's some tiny small constant. And in dimension 3, it's also W bigger than a small constant n3 C. Then you prove that, then one can show that the local statistics of the Bau eigenvalues will match the GUE, so the universality eigenvalues hold. And the other one is the eigenvector are actually completely delocalized in the sense that the super infinity norm is less than n3 minus 1. And so in the case of band matrices, the problem of delocalization was pretty much understood. And but the original question of Anderson is still open. And so this was the open question, main key open question in this direction now. Okay, so I'll stop my talk here. Thank you.
Question, just ask.
Yes.
Entries you always have.
Oh, we assume the entry are Gaussian. We assume entry, but actually, I think whether the entries are Gaussian or not is still not the key question, because the key question now is to understand you want the matrix to be as skinny as possible, but it still has the property that you can like a fat matrix. So to put it in a very simple way is how skinny can you push the matrix, but you still have the property of matrix still look like a fat one. That's really the key question. And what Anderson claimed is that you can have it randomness only on a diagonal, and everything else you can just add a little bit deterministic one. Then it still has this random. You still have these delocalizations. And what we prove for the band matrix in dimension 3, this W has to depending on the size by entering some tiny constant. So we still cannot do this. It's just exactly on a diagonal. So there's some distance. And the question is always that whether the mean field model is really good for non-mean field thing. And the reason because all the physical law are non-mean field. And then, but everything you can compute are the mean field. So you want to merge this, you want to close this gap, and this is what we are trying to do. Okay.
Any other questions?
Thank you.
I'm actually curious about the 69 thing that you mentioned.
Yeah.
So,
oh, it was because you computed, and then the Tracy-Widom law is a special function. It's an array function or whatever. You can compute it explicitly. So once you prove the second eigenvalue has a probability law, then you just look at its distribution. You compute what's the probability is less than 0 actually. And the probability less than 0 is I think it's 81% or something. But then you have a lambda 2 and lambda n. So you square them. Then you find it's 69%. And so let's say so the reason Sana believe that almost no random derivative graph are Ramanujan because he using algebraic method. He believed that without only the algebraic method can show the existence of Ramanujan graph. So that's why he believed that there's no random derivative graph are Ramanujan. On the other hand, alone was he's combinatorics, so he's closer to probability, and he felt that from his theorem he felt that it would be nice that all of them are all of them are Ramanujan. But actually, because the second eigenvalues is satisfied the Tracy-Widom law. So actually, once you compute it, it's really exactly just 69%, and so that's the answer. Yeah. Okay. All right. Thank you.